Alright, hello everybody. So today we're going to be talking about the comparison tests. So I'll say here, when we learned about improper integrals, we learned the comparison theorem. Right, so we learned the comparison theorem for improper integrals, which said suppose f and g are finite, or sorry, that's not what I meant to say, are continuous functions with f of x is greater than or equal to g of x is greater than or equal to 0 for all x greater than or equal to a. Then we had part A, which said if the integral from a to infinity of f of x dx is convergent, then the integral from a to infinity of g of x dx is also convergent. Right, so if the bigger function is convergent, then the smaller function better also be convergent. And similarly, we said if the integral from a to infinity, that's messed up the thing just on. So the integral from a to infinity of g of x dx is divergent, then the integral from a to infinity of g of x, or sorry, that's not what I meant to write, f of x dx is also divergent. Okay, so here we can say if the smaller function is divergent, then the bigger one better also be divergent. So we want to use this to, well, kind of like what we did with the integral test, we related the integrals in the series. So we want to figure out a version of this to work with series. So I'll say here, so the direct comparison test is the series version. Okay, so I'll say here though, in red, I'll say like the integral test, we need our terms positive. Okay, right, so we just need to be careful of that, but let's go through an example. So example number 1. So example number 1 is going to say, does the sum from n equals 1 to infinity of 1 over 3 to the n plus n converge or diverge? Okay, so let's write down here. since n is greater than or equal to 1, let's look at 3 to the power of n. Well, if n is greater than or equal to 1, this better be positive. So this is positive. So you can say that the fraction here, so n is greater than or equal to 1, so this fraction is definitely positive for all n greater than or equal to 1. Okay, so that's what we're looking for. We said that we need all of the terms to be positive, so we actually have that. The next thing to notice here is if we drop the plus n from the denominator, the denominator gets smaller. So what does that mean about the actual fraction? Well, so the fraction gets bigger, right? Because if the denominator gets smaller, that means that the fraction is getting bigger. So we're going to get that 1 over 3 to the n plus n is going to be strictly less than 1 over 3 to the n. So we could try to find this, we could try to analyze this series and see whether it's convergent or divergent, but instead we can try to work with this thing, which looks a little bit simpler. So the question is, are we better off looking at the sum of 1 over 3 to the n? And the answer is definitely yes, because this thing is simpler. So here the answer is yes. And the reason for that is that 1 over 3 to the n, if we want to try to rewrite this as a geometric series, remember this power needs to be n minus 1. So we can rewrite this as 1 over 3 times 1 over 3 to the power of n minus 1. Right? We can just pull out one of the copies of 1 over 3. Okay, so we can rewrite it in this form, and we can say here that the sum from n equals 1 to infinity of 1/3 times 1/3 to the power of n minus 1 is geometric. Right, because of the form a times r to the n minus 1. So we can say that it's geometric with, so figure out what a and r are equal to here, but a equals 1/3, because that's that part, and here that's r, so r equals also 1/3. Okay, so we can say here, since absolute value of r is less than 1, so I encourage you to fill in the rest of the statement here. But remember what we did with the geometric series. Whenever the absolute value of r was less than 1, we said that the sum of 1/3 times 1/3 to the n minus 1 is convergent, since the absolute value of r is less than 1. And moreover, we said that the sum from n equals 1 to infinity of 1/3 times 1/3 to the n minus 1, we said that that's equal to a over 1 minus r. Right, so we just write what this was equal to. This is 1/3 over 1 minus 1/3. And if we write that, that's actually 1/3 over 2/3. But now you just multiply both sides by 3 to get rid of the fractions on the inside. Then if you do that, you're going to get 1/2. Right, so we figured out that this sum is actually equal to 1/2. Okay, and now we're almost done with the problem here. So we got, where did my marker go? Here it is. So now we can say that the sum of this 1/3 times 1/3 to the n minus 1 equals 1/3 plus 1/9 plus 1/27 plus 1/81 and so on, right? We just take the powers as 3 in the denominator. And we said that this was actually equal to 1/2. That's what we just solved right there, using the fact that it's a geometric series. Now let's also write the sum of what we cared about originally, which is 1/3 to the n plus n. So if we write out the terms of this, this is going to be 1/4 plus 1/11. Right, so I'm just plugging in n equals 1, n equals 2, n equals 3, and so on. So you're going to get 1/4, 1/11, 1/30. The next term would be 1/85. Dot, dot, dot. And now we just look at each of these terms and look at what's going on. Right? So 1/3 that's bigger than a 4th. 1/9 that's bigger than an 11th. 1/27 that's bigger than a 30th. 1/81 is bigger than 1/85. So eventually, since all of these terms on the top are bigger than the terms on the bottom, then this thing better be bigger than 1/2. Or sorry, this 1/2 better be bigger than whatever this sum is. So I accidentally wrote that, but right. So this whole thing has to be less than 1/2, since each of its terms here are less than the ones up here. So that's what we get. So what we got, so the sum of 1/3 to the n plus n is less than 1/2, which means the sum of 1/3 to the n plus n converges. Right. So we got what we wanted, right? So what we did was we looked at our original series. We said that looks a little bit too complicated. Let me take a series that looks a little bit better. So we took this series. Where did I write it? We took the series here. We took this series because that looks a little bit less complicated. We said, well, that's a bigger series, so if the bigger series converges, then the smaller series definitely also does converge. So we're essentially doing the comparison test, we're just doing it for series instead. So I'll say here, we used the direct comparison test in example 1 to determine that a series converges. Right, so let's actually write down the direct comparison test. Let me just use a new board here. So the direct comparison test. Okay. So what it says is, suppose the sum of an and the sum of bn, right? So we're taking two sequences a and b. We're adding together all of their entries, so the sum of an and the sum of bn are series. with positive terms and suppose an is less than or equal to bn for all n. Then what we can say is part 1, if sum of bn is convergent, right? So if the sum of the bigger series, if that thing is convergent, then the smaller series better also be convergent. Then the sum of ANs is also convergent. Okay. And part 2 is going to say if sum of the entries in sequence A, if that is divergent, so if the smaller series is divergent, then the bigger series better also be divergent. Then sum of Bn is divergent. Right? So it's pretty simple. It's just taking a series and saying, well, so we take one series and we say, well, the other one's actually easier to work with. So we take a, in this case, bigger series. If we prove the bigger series is convergent, then the smaller series is convergent. If we take a smaller series than our original series and we prove that it's divergent, then our original series has to also be divergent. Okay. So that's kind of what I said there. I'm not going to rewrite that, but I'll say here, these are the two important things. The terms need to be positive, and every term in A needs to be less than every term in B, but here I say for all n. And I'm going to put a bit of an asterisk there, because that's not always going to be true. So what I'm going to say here is, kind of like what we did earlier, I'm going to say with ultimately decreasing when we defined it, I'll say the an is less than or equal to bn must be ultimately true. For example, to use the direct comparison theorem to show that the sum from n equals 1 to infinity of natural log of n over n diverges, that's what I meant to say there, we can compare it to something else, and let's compare it to the harmonic series. Which, remember, we said was the sum from n equals 1 to infinity of 1 over n. And we said here this thing diverges, so which diverges even though natural log of n over n is only bigger than 1 over n for n greater than or equal to 3. And I'll say here natural log of n over n is actually less than 1 over n for n equals 1 and n equals 2. Right, so what I'm saying here is, as long as after some point all of the entries in A are smaller than the entries in the sequence B, then we can use this, right? So I'm just saying, like for instance here, with this series, the first and the second terms of this series are actually smaller than 1 over n, but if we look at all of the rest of the entries, then this term here is actually going to be bigger than 1 over n as long as n is greater than or equal to 3. So essentially what we're saying is this is almost always bigger than 1 over n, so if we can prove that this is divergent, then the bigger thing is also divergent. Okay. So what I'll say here is, with using the direct comparison theorem, how do we find the comparison series? Right, because here I just kind of guessed that the comparison series should be 1 over n given our original series, which was natural log of n over n. So how do we figure out what it should be? Our answer here is most often you will use either most often we're going to use either number 1, which is going to be a p-series, which we said was the sum of all of these 1 over n to the power of p's. And we said this converges if p is greater than 1, and it diverges if p is less than or equal to 1, right? So one of the tools is the p-series. So we said, we looked at this term right here and we said, well, that looks kind of similar to a p-series as long as we replace the numerator with 1, and then 1 over n is of this form, 1 over n to the p. So if we can get it to look like a p-series, that's probably something we should do. And the second tool here for the comparison is a geometric series. So if we can get it to look like a geometric series, that's something else we'll try to do. So this looks like the sum of a times r to the n minus 1, which converges if the absolute value of r is greater than 1. That's not what I meant to say. Is less than 1. That's what I meant to say. And it diverges if the absolute value of r is greater than or equal to 1. Right. Okay. Now, I'll say here that you have to be very careful whenever you're using this test. So the reason you have to be very careful, if the smaller one is convergent, if you have two series and you say that the smaller one is convergent, then that actually doesn't tell you whether the bigger one is convergent, right? If I said let's say we have the sum of 1 over n squared, if that's convergent, that doesn't tell us anything about the sum of 1 over n, because 1 over n is actually bigger than 1 over n squared for large values of n. So telling you that this is convergent, so let's say we prove that this is convergent, well, that doesn't tell us anything about whether this one is convergent, because this one is bigger, and it turns out that actually this one is divergent. Right, so if you try to use the comparison test there, well, first of all, it doesn't work, because that's just not what it says there. It says if the bigger one is convergent and the smaller one is convergent. It doesn't say anything about if the smaller one is convergent, what happens. In this case, we got the smaller one is convergent and the bigger one is divergent. So if the smaller one is convergent, and if the bigger one is divergent, then that tells us nothing. Right, so you have to be careful there. Okay. I.e., we can't make any conclusion about the other series using the direct comparison theorem, right? So we're not always able to use this, direct comparison test is what I meant to say. We're not always able to use the direct comparison test. You have to be very careful with that type of thing. So let me write down another example to show you why this is the case. Okay. So let's write down here, consider the sum from n equals 1 to infinity of 1 over 3 to the n minus n here. Remember, we want to make it look like a geometric series or a p-series, right? So one of these two. And we say, well, if we get rid of this minus n, then it's going to look like a geometric series. So here, 1 over 3 to the n minus n is greater than 1 over 3 to the n. So the fact that the sum of 1 over 3 to the n converges tells us nothing about the sum of 1 over 3 to the n minus n, right? Because we're saying that the smaller one converges, so we don't know anything about the bigger one, right? So I'll say here, so we can't easily use the direct comparison theorem. So we're going to need a different, direct comparison test. So we're going to need a different test. So we use a variant called the limit comparison test. Right, so we're going to just use a different version called the limit comparison test. So let me write down here the limit comparison test is going to say, suppose the sum of an and the sum of bn are series with positive terms. If the limit as n goes to infinity of an over bn is equal to c, where c is a finite positive number, meaning that 0 is less than c is less than infinity, then either both series converge or both series diverge. Right, so this is a very useful tool because as long as we satisfy the hypothesis here, then as long as we know that one series converges, then the other one does, and if we know that one series diverges, then we know the other one does as well. So this does end up being very useful. So let's say example number 2. Let me just use the new board here. Okay. So example number 2 says, does the sum from n equals 1 to infinity of 1 over 2 to the n minus 1 converge or, sorry, I was supposed to say or diverge. Okay, so we're trying to figure out whether this series converges or diverges, and we're going to try to use this limit comparison test. So we'll say here, since the sum of 1 over 2 to the n is easy to work with, we'll use it for a limit comparison test. Okay. So notice here that this 1 over 2 to the n is a geometric series and because remember we can rewrite this as 1/2 times 1/2 to the n minus 1. So here we're going to get that the absolute value of r is equal to the absolute value of 1/2, which is 1/2, which is less than 1, so it converges. Right? So we get that this series is going to converge. Note that 1 over 2 to the n is less than 1 over 2 to the n minus 1, so the direct comparison test doesn't tell us anything. Right, because we're saying that the smaller one is convergent, that doesn't say anything about the bigger one. Okay, so we're going to try to use the limit comparison test. And to use it, we need to satisfy this condition right here. So let's go ahead and say let an equals 1 over 2 to the n minus 1 and bn equals 1 over 2 to the n, then c is going to be, as we said here, it's equal to the limit as n goes to infinity of, we said it was an over bn, so 1 over 2 to the n minus 1 over 1 over 2 to the n, right? So I often write the parentheses just to make it clear what we're doing with this fraction. So we're dividing this fraction by this fraction, and if we want to get rid of the fractions, then we just need to multiply both sides by something to get rid of the denominator fraction. And the way we do that is to multiply both sides by 2 to the n. So if we do that, we get the limit as n goes to infinity of 2 to the n over 2 to the n minus 1. Okay. And now we've got to say, well, normally how we solve these things, if we have polynomials up here and down here, is we divide both sides by the biggest power of n in the denominator. Here this is technically an exponential, but we're going to use the same concept. We're going to divide both sides by this 2 to the n to try to make things a little bit nicer for us. So we're going to rewrite this as the limit as n goes to infinity of, so we divide both sides by 2 to the n, so the numerator divided by 2 to the n is just 1, the denominator, this divided by 2 to the n is 1. And this divided by 2 to the n is going to be 1 over 2 to the n. Right, so I just divided everything by 2 to the n. And now you get to here. And you're saying that n is going towards infinity. So if n is going towards infinity, this fraction, what is this going towards? Well, this is going towards 0. Because you're dividing by a really big number, so it's going towards 0. So this limit, since this is going away, is going to be equal to 1. So c is actually equal to 1, and here we just needed to check that c was a finite positive number. And here it turns out that it is. Okay, so we can say here, since the sum from n equals 1 to infinity of 1 over 2 to the n converges, and the limit as n goes to infinity of an over bn equals 1 is positive and finite, then we can use the conclusion of the limit comparison test. We can conclude what it says is if one of them is convergent, then the other is also convergent. So we can conclude that the sum from n equals 1 to infinity of 1 over 2 to the n minus 1 converges. Right, and that'd be our answer. Okay, so so the trick there that we're using whenever we're trying to find okay, let me write this trick down actually on the next board, because we'll need it for the next example. So what I meant to say is this is a trick for the next example, but for the next example, a trick for finding your comparison series it's going to be when applicable take the highest power of n in the numerator and denominator. Alright, so this is something for the next example. So let me write that down. Example part A, we're trying to find whether the sum from n equals 1 to infinity of n plus 1 over n cubed plus n. We're trying to figure out whether this is convergent or divergent. So I'll say here let an equal n plus 1 over n cubed plus n. Okay, so as I said up here, we take only the highest power of n in the numerator and denominator because we're trying to convert this into a geometric series. So I'll say here, taking the highest powers in the numerator and denominator, we'll take, so just take the highest power terms, so Bn is going to be equal to the highest power term in the numerator, n, over the highest power term in the denominator, which is the n cubed. Okay, and we can rewrite this as 1 over n squared. And this, we can say, well, I think earlier I said geometric series. What I meant to say is p series. This is now a p series, is what I meant to say. So we can write this now as a p series. The second series is going to be a p series. So I'll say here, the sum from n equals 1 to infinity of Bn is going to be equal to sum from n equals 1 to infinity of 1 over n squared, which we said is a p series, and is convergent since p equals 2 is actually greater than 1, right? So we said whenever we had the p is greater than 1, then it's convergent. So this second series is convergent. So this is a convergent series if we can prove that that number c is positive and finite that we had in the limit comparison test, then we can prove that this series is actually also convergent using the limit comparison test. So we now need to figure out what c is equal to. So we said that the limit is equal to the limit as n goes to infinity of an over bn. So we're going to have n plus 1 over n cubed plus n over 1 over n squared. Okay. So I don't like fractions inside of fractions, so I'm going to try to get rid of the fraction in the denominator by multiplying both sides of the big fraction by n squared. So I encourage you to try to work out this limit on your own. But this is going to be the limit as n goes to infinity of n plus 1, or, oh, shoot, sorry. So we need to multiply this fraction by n squared. We're multiplying the bottom by n squared. That's just going to cancel out. We're going to multiply this fraction by n squared. So we're going to get n squared times n plus 1 over n cubed plus n, right? Because if you multiply a fraction by a number, you're actually multiplying the numerator by that number. Okay, so this is what we get. We can then distribute. So this is the limit as n goes to infinity of n cubed plus n squared over n cubed plus n. Okay, and remember the way we solve these limits is we divide both sides by the highest power of n in the denominator. So we're going to do that. We're going to get the limit as n goes to infinity of, so divide both of them by the highest power of n in the denominator, which is n cubed. So we divide the numerator by n cubed, we get 1 plus 1 over n. We divide the denominator by n cubed, we get 1 plus 1 over n squared. And remember that n is going towards infinity, so this is going away, and this is also going away, because the denominators of those fractions are getting infinitely big. Now we're just getting 1 over 1, so our answer here is 1. So our constant c is actually 1, which is positive and finite. That's what we were looking for. So I'll say here, since the limit as n goes to infinity of an over bn equals 1 is positive and finite, and our other series, which was the sum from n equals 1 to infinity of 1 over n squared, is convergent, the limit comparison theorem gives that the sum of n plus 1 over n cubed plus n is convergent. Right. So again, we just needed to figure out this constant. Since this is positive and finite, we can use the limit comparison theorem to say, since one of the sequences is convergent, the other one is also convergent. Okay. Now let's just do one last example here. So our last example, which is part B, is going to say that we have the series, the sum from n equals 1 to infinity of 1 over square root of n squared plus 1. Okay, so again, remember we're trying to convert this into either a p-series or a geometric series. So we can say, well, the way we would do that is maybe if we get rid of this plus 1, and that would actually fix things up a bit. So I'll say here, we'll take Bn equal to 1 over the square root of n squared, just by getting rid of that plus 1, which is the same thing as 1 over n. Okay, so that's going to be our Bn. And I'll say here that the sum of all the entries of Bn is going to be equal to the sum from n equals 1 to infinity of 1 over n, and we said that's the harmonic series. Which we know is divergent. So if we're actually able to use the limit comparison test, then the fact that this one series is divergent means that this other series is also divergent. Okay, so now we just need to compute that constant and see whether it's positive and finite. So the limit as n goes to infinity of an over bn. This thing here we're going to say is an, so we're going to have 1 over square root of n squared plus 1. It's a bit messy, but it's supposed to say that 1 over the square root of n squared plus 1 over, so that's our top, and the bottom fraction is going to be what we said here, which is 1 over n. Okay, now we want to get rid of that fraction in the denominator, so I'm going to multiply both sides by n. So we're going to get the limit as n goes to infinity of n over square root of n squared plus 1. Okay. Now, oh, sorry. Yeah, that's actually not what we wanted to do. So usually what we want to do is just get rid of the fraction inside of the fraction. But what I'm going to do here actually is to say, well, we can rewrite this as, oh no, that is, okay, I'm confusing myself, but this is the limit as n goes to infinity of n over square root of n squared plus 1. That's what we get. But we will actually want to move this n into the inside of this. So what I'm going to do is divide both sides by n, and if we do that, we're going to get the limit as n goes to infinity of 1 over square root of n squared plus 1 over n. Right. So the whole idea is that I want to get this n on the inside of the square root. Because if I do that, we're going to rewrite this as the square root of n squared plus 1 over n squared. Right, so if I move that n into the inside of the square root, all I need to do is make sure to square it, because now if you took the square root, it's the square root of the numerator over the square root of the denominator, you get back to what we started with. Okay, so the whole purpose of doing this is now we can divide both terms by n squared, so we get the limit as n goes to infinity of 1 over square root of 1 plus 1 over n squared. And now, finally, we can actually solve our limit. Because 1 over n squared as n goes to infinity, this is going to 0. And now you're just getting 1 over 1, which is again going to be 1. Right, so actually our constant is positive and finite. So that's what we wanted. So since the sum of 1 over n diverges, and the limit as n goes to infinity of an over bn is positive and finite, then we get that the sum of 1 over the square root of n squared plus 1 also diverges. By the limit comparison test. So just looking back at what we did for this problem, we took our original series, we said that's a little bit too complicated for us to solve whether it's convergent or divergent, so we'll simplify it a little bit. We can definitely tell whether this series is convergent or divergent because that's just the harmonic series, so that's divergent. And now in order to use this limit comparison test, we just need to find this constant. So we took this, and we said, well, we don't like fractions inside of fractions, so we got rid of the fraction inside of a fraction. And I actually want to get everything involving n actually inside of the square root. So I divided both sides by n, and then I got this inside of the square root by squaring it. And now that I've done that, now we can actually find this limit because this part is 0, and we got 1. So now we can use the limit comparison test, since this constant is positive and finite, to say that this diverges, so the other sequence must also diverge. Okay.